Recording in progress.
Hey everyone, so we will be doing homework 2 from we'll be doing homework 2 problems. All right, so our first problem was find the corresponding symbols for the ASCII code. So the first one is 24H. This H means hex. So we want to know what's the corresponding code, ASCII code of 24H is. This one is pretty simple. We can just go to Google and find ASCII table. So look at here. There are decimals, hexamals, like whatever. We're looking for hex 24, which is right over here. Hex 24. That corresponds to a dollar sign. So this means 24 hex is a dollar sign. Again, I used the ASCII table to figure that one out. 24 hex is dollar sign. The next one is 44 hex. Again, we'll just look up the table. 44 in hex is capital letter D. So be careful about the capitalization because it does matter in this case, because a capital D and a smaller d are two different things to computer. Okay, the third one is 50H, which means 50 hex. If we look up to the table, 50 in hex is equal to capital P. Let me see something. 50 in hex is capital P. And the last one is 75H. If we look up the ASCII table, 75H is letter U, but a smaller one, not the capital one. So these ones were pretty straightforward. I don't think these need any further explanation.
Recording in progress.
Okay, so our next problem, that one is kind of tricky one. So for that one, we have to convert the numbers to a real data format. What is a real data format? Basically, we follow IEEE 754 floating point precision format. And what's that? You can just Google it. IEEE 754 floating point. If you Google that, you can just look at this image. So this is the IEEE 754 floating point standards. So basically, we have one bit for one sign bit, then we have 8 exponent bits and 23 bits of mantissa. Okay, so we'll solve it. This way it'll be much easier for you guys to understand what I'm talking about. So our first problem is +9. We have to write that in IEEE 754 format. All right. So in order to do that, first of all, we know that there are, let's write the IEEE format. We know we have one sign bit. This is sign bit. and we have 1, 2, 3, 4, 1, 2, 3, 4 exponent bits. Then we have a bunch of blah, 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 blah. Mantissa. So we will solve them one by one. So first of all, if we look at this, this is a plus 9, right? So plus 9 means the sign bit is a positive. So whenever a sign bit is a positive, whenever there we have a positive number, the sign bit always is going to be a 0. So if it's a negative number, it's the sign bit is set to 1. If it's a positive number, the sign bit is set to 0. So it's pretty simple, right? Positive 0, negative 1 for a sign bit. Awesome. Now we have to find the exponent. Okay. In order to do that, we have to normalize this number and normalize into like, you know how we have scientific notations in decimals? Like if I have a number, let's say 123, in scientific notation, it'll be 1.23 into 10 to the power of something, 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 right? That's how we normalize in decimals. We have to do the same thing for 9, but in binary. So in order to do that, we have to first convert 9 decimal into binary. We already know that 9 decimal to binary, we have to find that, right? So we can just do our method 9 divided by 2. 9 is an odd number, so we'll just put 1 here. Then we know 2 multiplied by 2 multiplied by 4 is 8, right? So we'll do this over here, then 2 right here. Again, even number 0. So we'll get 2 here, 2, even number 0, 1, 2. It's an odd number, so 1, 0. So 9 in decimal is 1001 in binary. Now we have to normalize it. So which means we can write 1001 as 1.001 into 2 to the power. Since we moved decimal from this point, 1, 2, 3, 3 points, right? So we'll write 2 to the 3. This is the normalized form of 9. This one is all right? It's understandable. All right. Now, we have to find the exponent bits, right? In order to do that, what we're gonna do, okay, I'm gonna be real honest with you guys. At this point, we do something that even I have no explanation for. I just know we do this. So, like, in my last year of computer engineering, and even a senior doesn't know why are we gonna do what are we gonna do right now. I guess I just memorized it now, so I would say just memorize it. So to find the exponent bit, we gonna do this to find exponent. We're gonna do 127, and again, I have no idea why it's 127. I know it's 127. That's it. I have no idea why it's 127. And then we're gonna add 2 to the power of whatever that number is to that 127. 127 plus 3, that's 130. All right, this is, we're gonna convert this 130 to decimals. This is in decimals, we're gonna convert that to binary. So we can do that easily, right? You know what? I'm not gonna waste your time doing that because I know you guys can do it. So I'll just write it down for you. So 130 in binary are 1. Let me do 2, 3, 4, 0. That's our number. So that's 130 in binary. All right. So our exponent will be these number. This 130 in binary will be our exponent to find exponent. So we can just copy it down over here. 1, 0, 0, 0, 0, 0, 1, 0. So this was pretty straightforward, right? Besides the fact that we add, so, okay, let me summarize what we did until now. We find the sign bit by just looking at the number. If it's a positive, we're going to put 0, all right? To find the exponent, we have to normalize this 9 in binary. We did that. This is our normalized 9. Then we're going to add this 2 to the power of whatever thing is to 127. Whatever that number is, we're going to convert that into binary, and that will give us the exponent bits, the 8 exponents bit to our number, which is this. Now, the last part, it's called mantissa. Mantissas are pretty simple. What do I mean by that? So mantissa is going to be everything after point. In the normalized form, when we normalized 9 to something, anything after the decimal, after the point, is our mantissa. So in this case, we have 0, 0, 1, right? So we can write 0, 0, 1. And the other bits, the other remaining 20 bits, because mantissa is a 23-bit number. So other 20 bits gonna be just 0. We can just put them 0. I think this is pretty straightforward, but we'll do another problem. This way, we can learn more about it. Okay, on to the next problem. The next problem is negative 12. All right. So we know the IEEE format says that we have a bit for sign bit, sign. We have 8 bits for exponent, and then 23 bits for mantissa. All right. So since we just, let's look at the number. This is a negative number. And as we talked earlier, if it's a negative, the sign bit gonna be 1. If it's a positive, the sign bit is 0. If it's a negative, sign bit is 1. So we can just write this as 1. Awesome. Now, to find the exponent and mantissa, we have to find 12, just the magnitude of the number, decimal, into its binary form. I'm not gonna bore you guys with the calculation of this, so I'll just tell you that 12 in decimal is 1100 in binary, if that makes sense. I'm pretty sure you guys know how to do this, and if you are struggling with the conversion from decimal to binary, you should email me or get in touch with me so we can go over that and learn more about it. And if you're hesitant to email me, then you can watch our previous video on homework solution 1, because I think I explained that in details in that video. But okay, so 12 in binary is this. Now we have to normalize this number. To normalize it, we have to just write it like 1.100. So we moved the decimal 3 times. So 2 to the power of 3. That's the normalized form of this number. All right. Okay. Now, to find the exponent, we're going to do something that I don't have any explanation for. We're going to do 127 plus whatever this number is, whatever 2 to the power of something is, we're going to just add them. So 127 plus 3 is 130, which is actually 10000010 in binary. Okay, we did this. Makes sense. Now, this will be our exponent bits. So after doing the normalization, you're gonna add 2 to the power of whatever that exponent is. And that makes sense. That's why it's called exponent, because we are adding the exponent of 2 to 127 to get this number. And this number, since was obtained by using the exponent of 2, will give us the exponent. Does that make sense? I think that will be an easier way for you guys to remember that the after doing normalization, the exponent of that normalized number will help us getting the exponent bits of this number. Okay, so after all, we can just put these values here: 1 0 0 0 0 0 1 0. That'll be our exponent bits. And for mantissa, we're just gonna use whatever the number after decimal is. That will give us the mantissa. Hold up. As I was saying, we find the exponent to find the mantissa. Mantissa is pretty straightforward. Whatever the numbers are after the decimal is our mantissa. In this case, it's 1 0 0. So we'll just write 1 0 0, and the rest bits will be 0. That's it. That's how you find mantissa. Let's do another problem so that can help us understand this concept. Okay, so the next one is pretty kind of different from the one we just had, we dealt with. This is our next problem. All right, so let's just write the format sign bit. Exponent bits. And this all right, so we know that it's a positive number, so we'll just write 0 here for the sign bit. That's pretty simple. Now we have to convert this number to binary. I mean, we know how to convert 25 to binary, but do we know how to convert 0.25 to binary? It's kind of different method. So in order to convert 25 to binary, we divide it by 2, right? But in this case, since it's 0.25, we're gonna multiply by 2. So what do I mean by that? So we're gonna have 0.25, we're gonna multiply this number with 2, which gives us 0.5, right? So the first bit over here is 0. So we're gonna write 0. Now, whatever the remaining number is, 0.5, we're gonna multiply by 2 again, which gives us 1. So which is not a point, which is not a decimal number anymore, like which is not a 0 point number anymore. It's 1.0, and that's it. Once we get 1, we stop. That's it. So this means 0.25 in decimal is equal to 0 is 0 in binary. Then we're gonna add a point, and 0.25 is 0 and 1. I got this 0 from here and this 1 from here, if that makes sense. I think it's I think that's pretty easy, right? Like there is nothing special I did. Just remember, if we just have a number which is greater than 1, greater than 0, actually, which if it's a whole number, it's not a fraction, then we divide. But if in order to solve the fraction part of a number, we multiply by 2. So if it's 25, we divide by 2. If it's 0.25, we multiply by 2 to find the binary conversion. So 0.25 in binary is, this is 0.25 in decimal, 0.25 decimal in binary is 0.01 in binary. All right, now we have to normalize this number. In order to normalize it, we have to move the point 2 times, right? So it'll become 1.0 multiplied by 2 to the power of -2. All right. Now, once we have the normalized number, we can just simply do the same thing we've been doing, the same thing that I have no explanation for. So we're going to do 127 plus, we're going to add the exponent, which is -2 in this case. So this means 127 minus 2, which is 125. And this number in binary is 0, 1, 1, 1, 1, 1, 0, 1. So this will be our exponent. This will be our exponent bit. So we can just write these number over here. So we can just say that exponent bit is 0, 1, 1, 1, 1, 1, 1, 0. Actually 0, 1. Right? Yeah. Yeah, 0, 1. So that'll be exponent bit. And we know mantissa is anything after the normalized point. So in normalized form, anything after decimal is mantissa. In this case, it's 0. So which means it'll be 0. And the other bits that we don't know from here are going to be 0. There you go. So that's our IEEE format for 0.25. Now let's do the last problem. I think it's the last, right? Yeah, that's the last one. Yeah. So the last problem is -10. Let's do our thing. Sign bit. 1, 2, 3, 4. 1, 2, 3, 4. That's our exponent bits. And 1, 2, whatever, like 23 bits for mantissa. Okay, we have a negative number, right? So that we know if it's a negative number, the sign bit is gonna be 1. That's pretty simple. Now we have to then we have this 10 in decimal. We have to convert that to binary, which is pretty simple. 1010. I would not waste our time on this conversion. I'm pretty sure you already know how to convert a simple number to its binary form. Okay, now we're gonna normalize this number. So we're gonna do 1.010. We move decimal 3 points. So this means 2 to the power of 3, right? Okay, now this is the normalized form. Now we're gonna do the thing that we have no explanation for. We're gonna add 127 plus the exponent, which gives us 130, which is 10000010 in binary, and this will be our exponent bits. So we can just write that down. 10000010. That's our exponent bits. And at last, we have to find the mantissa. Mantissa is gonna be everything after the point in normalized form, so which is 101, right? So we can just write 0, 1. Actually, yeah, we can write 010, 010 in the mantissa, and there are nothing more after this 0. So we can just add zeros for the rest of the bits. So that's it. That was our homework too. I hope you guys understand it. And I'll just review through it real quick. So we did these problems. The first problem, it was just looking up the table and finding the corresponding values. Then for the second part of the problem, second part of the this homework solution, we have to convert the numbers to their IEEE 754 format. IEEE 754 format means there is one sign bit 8 exponent bits and 23 Mantissa bits. Sign bits are simple. If it's a positive number, you have a 0. If it's a negative number, you have a 1. For finding the exponent and Mantissa, we have to convert the number to its binary form, and from binary we're gonna convert that binary form to its normalized form, which will look something like this. And in that normalized form, whatever the exponent of 2 is, you're gonna add that number to 127, whatever that number is. In this case, it was 3, so 127 plus 3 gives us 130. We're gonna convert 130 into binary. That binary of that exponent plus 127 will be our exponent bits, and anything in the normalized form after the point will be our Mantissa, which is this. And we did something new, which was converting 0.25 to binary, which was a new thing for us. So since we have 0.25, we cannot divide 2 by 0.25. So we're gonna do 0.25 multiplied by 2. We're gonna keep doing that until we get 1 as a result. Once we get 1, we're gonna just go down and write the binary form like this. Remember, when we're doing the division, we count by the least significant. We start. You remember in the binary form, we go from bottom to up. If it's a regular number, but if it's a point something number, we go from top to bottom. And yeah, and then we're gonna do the same thing after that. So I hope this video helps. And if you guys have any question, feel free to ask me or email me. Thank you.